Accreting Tauri stars. Thank you.
Brilliant, thank you very much. So yeah, my name is Lewis Ireland, and I am a postdoctoral research fellow with the Awesome Stars group at the University of Exeter. And today, yes, I'll be talking about the magnetic braking of accreting Tauri stars. So just a quick introduction into the rotational evolution problem. So Adam Finley went into this in quite a lot of detail, so I won't go into it too much. But essentially, pre-main sequence solar-like stars, such as classical Tauri stars, exhibit a rotational evolution that currently lacks a concise theoretical explanation. So you would assume that these stars are still actively accreting material from their disks in this phase, and also they should be undergoing gravitational contraction as well. So a naive assumption could be that these stars would spin up over time. But this is not the case. So observations actually suggest that over a few millions of years, the spin rate distributions are fairly constant or can even show a spin down configuration. So the big question is, what kind of mechanism can help the star remove this excess angular momentum during the pre-main sequence phase? So let's talk about star-disk interaction. So classical Tauri stars are known to be magnetically active objects, and it's theorized that the magnetic interaction between the star and the disk could help remove angular momentum from the system. And previous studies have shown MHD simulations with magnetic field lines that twist due to the differential rotation between the star and its surrounding disk. And this, in turn, can cause the field lines at mid-latitude to inflate and open. And this could end up opening up another mechanism for angular momentum exchange. So when we talk about whether a star is spinning down or spinning up, or whether it's in a spin equilibrium state, the global parameter that we're interested in is the net stellar torque. Now, in theory, there's usually two main contributions that are known to contribute to the net stellar torque. The first is accretion, so the material accreting onto the star can add angular momentum, which can spin up the star. But also you get stellar winds that can extract angular momentum from the star via open magnetic field lines, which would spin down the star. So if you were to want to achieve a spin equilibrium state, i.e. the net stellar torque is equal to 0, theory suggests that you would need a mass loss rate in the wind of about 10% of the mass accretion rate. However, this is unlikely achievable if powered by the star itself. So this brings me on to another mechanism that's been looked at in more recent MHD simulations, for example, those in Zani et al. 2013. And this mechanism has been coined magnetospheric ejections, or MEs. So what MEs are essentially is the opening and reconnection of field lines due to a buildup of magnetic toroidal pressure as a result of the differential rotation between the star and the disk. And this can help extract angular momentum from the disk and or the star, which in theory could give us a mechanism that spins down the star further. So the question is, are these MEs important in the rotational evolution of pre-main sequence stars? Okay, so we have actually performed a star-disk interaction parameter study. To do this, we used a modified Pluto code to simulate 2.5D magneto-hydrodynamic axisymmetric star-disk interaction. We have an initial dipolar field and a viscous/resistive accretion disk. And we investigate how the following parameters affect the net stellar torque. The first being the stellar magnetic field strength. The second being the mass accretion rate, which we change via the initial disk density. And finally, the stellar breakup fraction, which is a direct measure of the stellar rotation rate. Okay, so here is an example movie of one of our star-disk interaction MHD simulations. So I'll start with the one on the left first. This is the entire computational domain. So here you can see in yellow the accretion disk, and this is accreting material onto a star which is located here. Then you have these periodic inflation and reconnection events, which we coin the MEs. This is a result of the twisting of the field. And then we also have the stellar wind being ejected via the open field lines. The movie on the right is the same simulation, but just kind of zoomed in around the region where the material accretes onto the star. So here, again, you can see the accretion disk coming in. And then you can see here that the accretion actually splits off into these primary and secondary accretion funnels. This occurs at a place we call the truncation radius, which is typically where the magnetic pressure in the magnetosphere balances the pressure, the thermal disk pressure. Okay, so I quickly want to illustrate the qualitative behavior of this parameter study. So these images here are the computational domain again, just a snapshot where I've zoomed in around the vicinity of the accretion onto the star. So the top left is just a fiducial case, which I want to compare against. So let's start the top right. In the top right plot, I increased the mass accretion rate via the disk density. And as you can see, if you increase the mass accretion rate, you are increasing the thermal disk pressure, which is experienced at the magnetosphere, pushing the truncation radius closer and closer to the star. So an increase in mass accretion rate decreases the truncation radius. You can get the same effect by decreasing the magnetic field strength as shown in the bottom left. So if you decrease the field strength, you weaken the magnetic pressure that the disk experiences, so the disk comes closer to the star. And finally, in the bottom right, you can do this by increasing the rotation rate of the star, because this influences the differential rotation between the star and the disk. So what's fascinating about all of these simulations is the closer that the truncation radius is to the star, the lower the latitudes of the field lines that connect the disk to the star. And because you are connecting to lower latitudes, you are opening up more area for wind ejection. So this is quite a cool result because it's suggesting that the geometry of the star disk interaction, i.e. the presence of an accretion disk, can have an effect on the amount of open flux ejected in the wind. So why are we running these simulations? Well, what we want to do is be able to, like I mentioned before, determine the net stellar torque. So what we want to do is parameterize these torques using the parameter study. And why do we want to do this? Well, firstly, there would be no need to run additional simulations to determine the net stellar torque for a given set of input parameters. But also you can implement a torque formulation into a 1D stellar evolution code in order to, for example, evolve a pre-main sequence star over time to investigate its rotational evolution. Now, the net stellar torque in our simulations depends on three contributions. The first is the accretion torque, which is located here, the stellar wind, which is located in this vicinity, and then the MEs, which are between these red lines here. So how do you actually parameterize the torques? So I'll start with the accretion torque because that's quite straightforward. Analytical theory can parameterize the accretion torque via the mass accretion rate and the truncation radius. However, the actual values of accretion torque we achieve in these simulations are a fraction of what is predicted by theory. And that's because these MEs are removing angular momentum from the disk, which ends up causing the disk to rotate at speeds lower than Keplerian in the region of the truncation. Therefore, therefore the values of the accretion torque are about 70% of what's predicted by theory. And because we can parameterize the Keplerian accretion torque, the formulation is simply this expression here, which we show in this plot here to correlate really well with the values calculated in the simulations. So then we also have the stellar wind. So as Adam mentioned before in his talk, you can typically parameterize the stellar wind torque as the product of the mass loss rate in the wind, the stellar rotation rate, and the square of what is essentially the effective magnetic lever arm of the wind, which we call the Alfvén radius. And the alpha radius can be parameterized as the square of the open flux over the mass loss rate to some power that we fit semi-analytically. And again, the plot shows that for our simulations, we fit the formulation quite well. And what's pretty cool about our parameter study is that we are in a regime where the mass accretion rate is dominating over the mass loss rate of the wind. And when this is the case, the open flux in the wind is predominantly a function of the truncation radius. Therefore, the stellar torque can be parameterized in terms of RT. And this just goes back to the point I made before, where the presence of an accretion disk or the SDI geometry opens up more wind flux because you're connecting to lower latitudes, which means you have more open flux compared to, say, an isolated stellar wind case. And then finally, we have the ME torques. So the ME torques scale with essentially the extent of the magnetic connection between the star and the disk, which we can parameterize by the product of the differential rotation between the star and the disk, the square of the field strength, and the truncation rate to some fitted power. And again, our plot shows that we get a pretty good correlation. There is a little more scatter compared to the other fits, and that's just because these MEs are periodic in behavior. So we have to take time averages of these in order to get out a time averaged global parameter. But the fact that these are time averages and fit well is pretty promising. In all of our models in this parameter study, we find that the MEs extract angular momentum from the disk in a region rotating greater than the star, which means that even though the MEs are inhibiting the accretion torque, some of that spin-up torque is still going to the star in the form of ME torques. So now we have three torque formulations to work out the net stellar torque. The final thing we have to do is parameterize the truncation radius, because this is the only parameter in this formulation that we don't know a priori. So in theory, the truncation radius is typically parameterized as the square of the field strength over the mass accretion rate. And also in theory, the scaling is about 2/7 or 0.28. But we find a slightly steeper scaling than that, and that's because the accretion disk is actually perturbing the magnetosphere, which means that in the vicinity of the truncation region, the magnetic field isn't exactly dipolar, which just corresponds to this slight steepening of the gradient. But as you can see, again, we get a really good tight correlation for this. So now we are able to determine the net stellar torque from just 6 parameters we know a priori. So the stellar field strength, mass, radius, rotation rate, the mass accretion rate in the disk, and the mass loss rate in the wind. However, because the MEs are actually spinning up the star and the accretion dominates over the stellar wind, our parameter study is in the net stellar spin-up regime. Now, this doesn't really answer our question regarding how these stars can achieve either spin equilibrium or spin down over time. Therefore, we need to push our parameter regime into this spin down regime. So this is what I'm currently doing at the moment. I've run a bunch of new simulations, and what I've tried to do is push our simulations into what's something we call the propeller regime. So the propeller regime is when the truncation radius is pushed closer and closer to the co-rotation radius. The co-rotation radius being the radius in the disk which co-rotates with the star. To push this truncation radius outwards, you can either do it by increasing the field strength, or F, which just increases the magnetic pressure pushing against the disk, which pushes the disk outwards, or you can decrease the mass accretion rate, which just weakens the thermal disk pressure. However, in this regime, the simulations are a lot more dynamic and complex compared to when the truncation radius was much less than RCO. So this is another example of a more recent simulation. And as you can see, they're a bit more dynamic, and you can see that a lot of the accretion is actually inhibited by the co-rotation or the centrifugal barrier. So you can see a lot of the accretion being blown out, which means as the truncation radius goes further and further away from the star, you're actually inhibiting the accretion, and the mass accretion rate can actually tend to 0. Also, if the MEs extract angular momentum from a region of the disk spinning slower than the star, which would be the case outside of co-rotation, the MEs can instead spin down the star. So it's actually possible in this regime to achieve a net spin down because you're inhibiting the accretion, but also the MEs can spin down the star. So that's quite a lot. So I'm quickly going to recap the regimes that we've covered and how it affects the torque found by the star. So state 1, where the truncation radius is much less than the co-rotation radius, this is our first parameter study. The sum of the accretion torque and the ME torque experienced at the stellar surface is always contributing a spin-up torque. However, when we get into the propeller regime, which I will now split off into 2 different states, things change. So we'll start with what I've called state 2, where the truncation radius is less than our co, but approaching it, so the magnitudes are more comparable. You can either achieve a spin up, a spin equilibrium, or a spin down torque contribution from the sum of these torques. And this depends on the relative magnitudes between those 2 torques, but also the extent of how magnetically connected the disk is to the star, inside or outside of co-rotation. Then we also have a state 3, where the truncation radius actually exceeds the co-rotation radius. At this point, we know that most of the accretion is inhibited, and even if you get a non-zero accretion torque reaching the stellar surface, this will be negligible compared to the ME torque. And because we're outside of the co-rotation, the MEs are extracting angular momentum from a region in the disk which is spinning slower than the star. Therefore, they produce a spin down torque contribution onto the star. So this new regime has a profound effect on our torque formulations. We have to recalculate them in order to make them more general for across the parameter studies. But rather than go through
3 minutes.
all of the parts again, okay, thank you. Rather than go through those parts again, I thought I'd just quickly touch on how it affects our parameterization of the truncation radius. So as I showed before, the first parameter study, when RT is much less than R co, you can parameterize RT simply as a square of the field strength over the mass accretion rate to some fitted power. And that is this black line here. However, in states 2 and 3 in this propeller regime, when RT is more comparable to R co, you see a complete divergence from this scaling. I mean, one reason why this occurs is because as you inhibit convection, the mass accretion rate will tend to 0, which would cause this term to blow up, essentially. Therefore, if you were to stick with this parameterization, you would be completely overestimating the truncation radius and therefore getting the torques completely wrong. So this is something we're currently working on, and we're very close to getting a result. So yeah, it's all very exciting. So just to summarize, we have, for a particular star disk interaction setup, we have successfully parameterized the net stellar torque on the star, which can help us predict the net stellar torque for given parameters, or also implement them into 1D cell evolution codes. In the first parameter study I discussed, all of these were in a spin-up torque configuration. We found that the MEs can reduce the accretion torque, but because they extract angular momentum from the disk where it's spinning faster than the star, this only just provides an additional spin-up torque. So in order to get around this, we're currently exploring a new torque formulation for the propeller regime. So this is just by increasing the truncation radius via a higher field strength or a higher spin rate or a lower mass accretion rate. But yeah, so we've actually managed to achieve a net stellar spin down in this regime, but the simulations are much more dynamic and complex, therefore more difficult to parameterize. But we are really close to getting a publishable result, so fingers crossed. Okay, thank you very much. Any questions?
Excellent. Thank you very much for that, Lewis. An excellent talk. Do we have any questions for Lewis? No, no one as yet. I got a, oh yes, Moira. Moira's got her hand up, so go for it, Moira.
Hi, Lewis. That was a really interesting talk. I really enjoyed that.
Thank you.
Do you have any insights into whether these states are like quasi-equilibrium states? I mean, I'm thinking of something like the FUREs, where you get these huge changes in the mass accretion rate with time. You may not be able to tell from your simulations. I don't know.
So the thing with these simulations is they only kind of cover a matter of weeks or months. So we're hoping for a particular parameter regime that we cover, that it would kind of cover different pre-main sequence phases depending on, yeah. So I'm not too sure really. That's not something I've really looked in, but I mean, we can kind of get a spin equilibrium state out of these simulations, but whether or not this is realistic over the timescales that we want, that's not something I'm really too sure about at the moment.
Well worth looking at, isn't it?
Yes.
Thank you.
No worries.
Any other questions? No, thanks again, Lewis. So